Pile, right in time. Okay, so I will not start by thanking the organizer for having invited me. And I didn't think about that by preparing the talk, but it will be somehow related to, especially to the discussion of last time by Michael, about modeling, in fact, the real, what is real in quantum mechanics. First of all, I'm going to talk about quantum mechanics. I'm going to talk about mathematics, in fact, although there will be no formula, basically, more pictures and things like this, but not picture illustrating mathematics, picture of which has nothing to do with mathematics. But what I will try to do is to present you basically all the mathematics you know in order to understand quantum mechanics, and to show you two things, in fact. First of all, that I think everybody here believes that there is no paradox in quantum mechanics. It's fortunate because the word is quantum, fully quantum. There is only a quantum theory. We are all quantum objects. The quantum theory is about 1 century ago. All the experiments have been done who prove that the formalism of quantum mechanics is correct, and this is something that it's very easy to check without any doubt. So we are quantum. And in a certain sense, the trouble with quantum mechanics is that each time people talk about quantum mechanics, they use classical mechanics words, language. And this is a total disaster. And I'm going to show you a little bit that. I'm going to show you already by the most famous animal who's tortured in order to explain possibly the problem of quantum mechanics is the famous Schrödinger cat that you found everywhere now. In any supermarket you have a Schrödinger cat now to buy, which go much beyond what Schrödinger had in mind. I mean, for Schrödinger it was probably just very little things, and now it become like the paradigmatic situation for quantum mechanics. And what I want to show you, my thesis in a certain sense is very pretentious, but we are between friends, so I'm going to say it, is that mathematics for quantum mechanics are not a language of quantum mechanics. They are fully the quantum mechanics. That is, it's not that you can express, like famous Galileo, in fact, didn't say it or didn't write it, that you can use mathematics as a language for quantum mechanics. You cannot use anything else, basically. That's the point. And for that would be, there are a lot of non-mathematicians in the room, you know, so if you hear that, you will just leave and follow. But the good news, according to that, we might think as bad news, is that the mathematics of quantum mechanics are extremely simple, much more simple than the mathematics for classical mechanics. And I will show you that, and I will show you that if I made the experience, with Giuseppe Lungo, a friend of mine and a logicist, to teach, I mean, not to teach, to lecture on quantum mechanics, and at the same time on the Gödel theorem, by starting from the scratch. And we did that for 7 lectures in front of 50 people in the basement of École Normale. And there were no mathematicians, no physicists, and everybody remains, and everybody understood what is quantum mechanics. Because for quantum mechanics, as soon as you know what the multiplication of number is, you're able to understand all the formalism of quantum mechanics. This is very different. Yesterday, Mario talked about, I don't know, come si dice in italiano, F equal m gamma. In French, we say that? Nobody understands this, right, in principle. Because acceleration needs to derive twice something. It's a nightmare, totally nightmare. Nothing like that in quantum mechanics. So be quiet, remain here, and I hope not to disappoint you. So, poor cat. It's not a question of knowing if the cat is dead or not. You know, I mean, everybody heard about the cat of Schrödinger, right? This situation situation where you have a cat which is at the same time dead and alive. Everything is wrong in this sentence. For example, the word is. The dead or the life is not something that you are on. It's, in quantum mechanics, it will become a property like another one. So that's not a question. And it makes a lot of trouble for explaining quantum mechanics to have this kind of picture, which has absolutely nothing to do with quantum mechanics. The real cat is the cat of Deluc, of Gay-Luc, sorry. And the cat, the relation of the cat with the death is exactly explained by this that I can read. I made the translation there. And this is the cat facing the death. And it has nothing to do with the cat of Schrödinger. So the paradoxes of quantum mechanics, you know, held by these people who always complain there are problems with quantum mechanics. You know, it's like social perception of some basic fact. Let me remind you, I didn't plan to say that, but the first TV show on homosexuality in France was in 1964, and it was, the title was Homosexuality, This Painful Problem. If you pose the things like this, obviously you have all the problems you want. So there is no problem in quantum mechanics, and in fact, the paradox you can have are paradoxical in the sense that they don't exist just. So I'm going to introduce all the mathematical tools you need to understand quantum mechanics, and they are exactly the same that what you learn in primary school, not talking about gymnasium. No. It's a plus and a multiplication. You know how to add numbers, you know how to multiply numbers. That will be a little bit more difficult, but it's very, very easy to understand, and you can understand quantum mechanics. So the first topic will be superposition, because you know superposition is exactly what people try to say. The cat is in a state which is a superposition of dead and life. Totally stupid. I will show you another experience of superposition you all got is when you go to see a 3D movie in cinema. Cinéma en relief, as we say in French. And in fact, I will make a little parenthesis to show you that in photography also, this was part of the very early birth of photography to try to get the third dimension. Then I will show you that will explain the plus. This will explain by a detour in music, and I might be beaten at the end, but why the multiplication has something to do with the musical notation, the one of Guido d'Arezzo, which is so powerful since 1,000 of years, and which now, a little bit, since a few decades, start to have problems. And then I will talk about entanglement. I will explain this, and I will show you that if you face the experience of driving a car when you have a plane to take and you're late, and you arrive at a crossing with a traffic light which is red, if you understand what you feel at this moment, you understand what is entanglement. Nothing more to understand. Laugh, laugh. So that's today, right? Tomorrow, in my course, I will do mathematics, equality, and all that. And I will start my lecture tomorrow by this quotation of Jacques Lacan, fini de rire. So laugh today, laugh today. Okay. So Hitchcock had been already mentioned by Jean-Michel on Monday. I'm going to talk about another picture, which is Dial M for Murder. In French, Le crime était presque parfait, which is, I think, the only movie by Hitchcock we see in 3D in the 50s. And it's the 3D in the 50s was exactly as the 3D now, except that we have no electronics, and the two pictures, which were the two images, which were projected on the screen, were just with some different polarization. You have these very light glasses, which helps you to recognize. So what is cinema in 2Ds? And it's nothing else than the way we have of looking at. We see the third dimension because we have two eyes. This is not correct, because if I do that, I still see you in 3 dimensions. But because I remember the 3 dimension. if you go to the 3D movie, for example, if you remember the scene, I don't know if you saw it, the scene in Le Crime était presque parfait, where Grace Kelly is on the table like this, and she's like this, so you, as a spectator, she's like this, and she tries to catch a knife or a scissor in order to murder the guy. You have the fingers of Grace Kelly on your nose, exactly when you're doing this. And if you just do that on the glasses, whoop, the fingers go back to the screen, and the third dimension is totally suppressed. So this is exactly what the superposition in quantum mechanics, because you have an addition, a plus. So let me write a plus. So you have a plus, which has nothing to do of being dead plus alive. It's a plus of two signals, different signals, which enter your eyes, and the superposition of it, which is done by your hardware here, give you exactly the third dimension. This was not new for this is not new for cinema. This was done. We have stereoscopic pictures. You know these things that when I was a kid, we were looking with an apparatus like this, and we're doing like this, pictures like this, were exactly contemporary from the birth of photography. That is in daguerreotypes of 1850. You have already these Doppel pictures, which correspond to the picture taken by two objectives at the space of the eyes, whose superposition gives you the impression of third dimension. In fact, it gives you the third dimension. And I put this kind of picture. So if you find it, if you print it, and you face the thing like this, and you put a piece of paper like this, you have the picture at 20 centimeters, then you have to focus at infinity, which means that's the difficulty. You have to go far, to look at far away for something which is at 20 centimeters of your eyes. But you succeed it, and you have the two pictures, which comes like this, and then you have the third dimension, which appear. This one is not beautiful only because the canon of beauty in 19th century were more suitable for third dimension, if I may so say so, o tempora o mores, in Arpino I should quote Cicerone. But you see, you have a woman, a naked woman that you see from the back, and you see what? Its image on the mirror. That's something extremely sophisticated if you think about it, because the image on the mirror is two-dimensional. If you write to me, I send you the PDF of this, and you do the experience, it's absolutely fantastic. So the morality of this, the morality of this is that this superposition of quantum mechanics has no equivalent in classical physics. But it has an equivalent, and a lot of them, in our perception of the world. Because the way we look at the third dimension is a superposition of two signals. And of course, looking at this, or at cinema, it's more efficient because it's more algorithmic in a certain sense. Because if you do that, I still see you in 3 dimensions. If I do that in front of Grace Kelly, the third dimension disappears immediately. So that's for the plus. Now let us try to understand the multiplication. The multiplication, so this is part of the score. This is part of Eroica, I think, from Beethoven. The Klangenfarmel melody with the oboe and then the clarinet, the flute, the violin. And you see that you have several instruments, and each plays some note. And that's more complicated, sorry. And the multiplication will be an operation which couples this one, the flute part, to the oboe flute. What I mean is that if you have, then it's better than I take the next one. This is an extract of Ravel's sonata for violin and violoncello. If you have a violin, we play an A, for example. And it plays together with a violoncello playing a D. What Guido d'Arezzo tells you is that you have to put them on 2 lines different. So the lines are like this in music, they are like that in mathematics, because in music the times go horizontally from the left to the right, even for Hebrew music, by the way. And in mathematics, the times go from top to bottom. That's the way it is. So I suggest that this, a play like this, which I don't know what this is, should be, should be understood as a multiplication of the violin note by a note played by the violoncello. You can write all the music like this. No interest, of course. No interest because when you have a lot of notes, like for example, in this extract of the Rite of Spring, you see, you will have a very long formula if you want to make completely. Okay.
Theoretical physicist.
Yeah. Thank you. And theoretical chairman, thank you. So, you see, this is just to tell you this, and then how do you couple? Oh, be careful.
Okay, go on.
Thank you. Okay. Now, if you suppose that you have, like it's one of this part, for example, you know this part, you have the violin which plays 2 notes at the same time. So how do you do to imagine that the violin, this is the only formula we're going to write. The violin is playing an A, for example, and the violin will play also a C. This is a plus sign. This is a plus sign. This is the definition of the plus. And actually it corresponds exactly to the addition of the pressure of the sound created by the violin on the string playing the A and on the string playing to the C. So it's a plus which is, in a certain sense, a plus, classical plus. And then, if at the same time the cello plays also 2 notes, for example, cello playing in D, that's not going to be very beautiful, but plus a violoncello playing an F, you will have something like this, and once again you can write everything. Very fine. Just a question of putting a notation, absolutely no interest. By doing this, you exhibit a structure in mathematics that you can very precisely define, which is a tensorial product. You call it a tensorial product, it's a product like any other product. But the tensorial product of the 2 spaces, the space of the violin by the space of a violoncello, then this is a huge set where the objects are not only on this form, but you can have also violin playing A, tensorial violoncello playing D, and all that plus violin playing D plus tensorial product violoncello playing G. Okay. Quantum mechanics likes symmetry. So if you give to quantum mechanics something like that, she immediately wants to do something where they permute the sign and everything should be possible in quantum mechanics. Quantum mechanics is a theory of freedom. Now try to imagine an equivalent of this in the notation of arrays. It's not possible. You're going to become completely crazy. You want to couple something which is already coupled and then to add, but the addition works only on each line, not between things which are already coupled. This is just impossible. So what quantum mechanics tell you is that this kind of state, if you want to talk about acoustic of music, is an accord inaudible. Not dissonant, but inaudible in the sense that inheardable chord. It doesn't exist. You cannot play it. And if you write something like this to a musician, What it has to do is to play this one or this one. Life, dead. You have a superposition here, and you have two chords which are very belonging now to the real space. You can play this. And you might say, this has nothing to do with music. It's not true. It's not true because in music in the 50s, and now probably all the musicians in the room will just kill me, in the 50s, this kind of work, where at one point of the work, of the score, the interpreter, the player, has to make a choice, himself or herself, between two possibilities, were called open works, and they were very fashionable as a big novelty in the 50s. It lasts for 10 years, and then they just disappeared, exactly like the daguerreotype in 3D disappeared after a few years and were reborn only in the 50s. But you see, a piece of the art, like music, which were considered as fantastic in the 50s, and nowadays is considered as something extremely bad, this cannot be bad. There is something for them. So what I'm just tell you, and I have to hurry up because I don't have so much time, is that what you need for quantum mechanics is just a very, very nice extension of what you use for music. An extension which is not really something that you can write on the notation of a razor, but it exists in a very natural way. So, in fact, this is an example of an open work. This is an extract of Éclat, a work by Pierre Boulez. And you see, in Éclat, I advise you to go to listen to it if it's played, if it's very rare played. At one moment, you have three instruments, I think, maybe four, who has a certain part of music that is a sequence of notes, which is on a circle like this, that is periodic, you know. And at one point, they don't know when they're going to start playing and on which note on the circle they're going to start. And it's the conductor who decides this, and you're supposed to decide at the last moment. That is, it show you, 3. This means that you start by your 3, like this. So it's totally open, and each execution of the work is totally different from another one in principle, because this order is changing all the time. Not only the order, but also the starting point like this. Of course, Boulez is an outstanding musician, but in contradiction with himself sometimes. So what he does, in fact, the three instruments, if I well remember, is the arpa, the cembalom, and the mandolin that we are going to see tomorrow. That is three instruments who basically make the same type of sound. So in fact, for the people who is listening, there is no difference between any kind of things. But Boulez explained that he did that in order to create a tension with the musician, because even a musician who plays very, very often contemporary music, when you don't know when you have to start and on which note you have to start, is extremely stressing, you know. So, okay. So if I had 1 hour more, I would explain you that a little bit more. But what's happening here is that you have a kind of object like this, which is out of the language of classical mechanics and which cannot reduce by no means to classical mechanics. This is, I take this very nice movie by Jean-Luc Godard, whose name is L'Adieu au langage, which is a movie in 3D, but with the virtuosity of Godard, we have a lot of things which happen inside, showing only one part, the other one. It's really a fantastic word. The important fact about this is that it's l'adieu au langage. Understanding quantum mechanics is really, you need completely to forget absolutely about the classical language. Otherwise, you don't go on. But you see, if it was just a theorem telling you that you need to forget about all the positivity means that the new language of quantum mechanics is at the same time mathematical and very close to our way of feeling the reality, like I'm going to show you now. Entanglement. typical catastrophic representation of entanglement. So what is entanglement? Entanglement is something which has been realized in Geneva, experimentally. Believe me, you take two electrons. An electron, what it is, it's a particle which has a spin. And the spin is something which is up or down. And you take two spins, two electrons, which are entangled in a certain way that you have a sum like this. That is, you say, once again, you see, it's the same formula. It's the same formula, except that you have Alice up here, tensorial Bob down, plus Bob up, tensorial Alice down. It's exactly the same formula. There is no mathematics more sophisticated than this. And then Bob and Alice don't get well together again, so Bob, he left. He leaves, and he leaves, that is one of the two electrons, or actually there are photons or not electrons, is sent to the other side of the Lac Léman. It's very stable. It's sent, in fact, by the line of Swisscom, of Telecom. In fact, as a physicist, I use the telephone line twice, one to send the photon, and second one to call back to say the result. You know? And if you send like this, if now you measure what is the spin of the Bob, if the spin is up, automatically if you measure the spin of Alice, it will be down. This means that if you make a measurement, and the measurement is exactly the way that you choose one of these two things, if you choose this one, you will get, if you get down at 500 kilometers, she will automatically get up. This is what people have said, that there is a transmission of information. There is no information transmitted. It's just a fact that you are facing a situation like this. This means that when you are on this side, this up gives you this down, or the contrary. Now, the representation we have is a total disaster. Because imagine that quantum mechanics has something to do with Bob Dylan in Wonderland. It's totally erratic completely. So sometimes people do a little bit better and say, oh, let us do something which looks more scientific. I think this is even worse than this for me. It has absolutely nothing to do with what's happening. It's just pure fantasy of imagination. It's beautiful, they're beautiful colors, but it has nothing to do. The true way of understanding what is entanglement is the traffic light. Alors, why is the traffic light? Well, what's happening if you go to Fiumicino and you're late and you arrive to a crossing and you get red for the traffic light? You say, the traffic light is red. Everything is wrong like this. First of all, the first word I didn't say. I'm not lucky, I'm unlucky. There is nothing to do with chance here, absolutely nothing to do. Secondly, it's not that the traffic light is red. It's that the red part of the traffic light is red, is unlighted. You know, traffic light, you have to, how do you say, the bubble, the electric bubble? These kind of things, l'ampoule. Huh? Bulb, okay. So, the electric bulb, you have an electric bulb which is red and an electric bulb which is green. It's not that the traffic light is red or green. It's just that the traffic light, the red one, is enlightened. It's totally different, you know. You don't put a property to the traffic light. You just say that one of the parts of the traffic light is enlightened. But the way we are thinking is not at all like this. Of course, in principle, we know that in the traffic light, there is a little machine which turns like this, and which makes succession of red and light, red, light, red and light. But it's not at all the way you consider this. You know, if you are really in a hurry, and if somebody next to you says, you know, not a question of luck, you know, it's just that we arrive at the moment where the machine was giving the red, you just pull you slam your face, his face, you know, her face, you know. The way we are believing, believe me, the way we are to look at the traffic light, looking at the traffic light is making a measurement of the traffic light, which will tell you that you go or you stop, is typically a measurement, and you feel it as if it's random, completely random, which is part of the quantum mechanics. So why do you pass when the traffic light is green? because you know that when the traffic light is green for you, it's red for the other. And if you are in a region of the world which is not too much in the south, you believe that people are going to stop if they arrive in the other direction. So once again, only one formula. It's exactly the formula. You have here us red, tensorial, them green, or us green, tensorial, they red. It's exactly the same formula, and the way you're facing this, facing the traffic light, is exactly performing this measurement, that is, where you feel, randomly projecting on this part or on this part. Nothing else. Of course, I have a hold, so I don't remember what I wanted to say. Yeah, okay, so you see, once again, if you consider a traffic light like something which is not as a real object subject to classical mechanics, the way you look at the traffic light is exactly something which is exactly in the quantum formalism. Alors, entanglement, I hope Michael and Stefan will forgive me. I'm going to use some borderline philosophical terms, like existentialism, just because I want to bring a little bit of Saint-Germain-des-Prés in Arpino. And you see, existence, what I feel is that when you look, the way of looking at a traffic light is more in something like lives in the existence, that something is in the essence. Is in the essence, you would say the traffic light is red. Not that I see the traffic light is red. But I have to hurry up, so I will be there. This is a very bad joke, but anyway, I stop it. And this is, I think I will arrive soon to my conclusion. Yeah, okay, very good. So this is where we got Bob Dylan in Wonderland. So what I was saying that the morality of all that is that, of course, you cannot explain all the quantum mechanics with a traffic light. I gave you something which is not an image, which is really something which touches the heart of quantum mechanics. Of course, after that, you have vectors. You have to multiply vectors by numbers, and you have a lot of mathematical machinery. But the essential is here.
In the south, you have traffic lights. It's green on one side, red on the other, presumably, but the observer doesn't care.
No. If I tell you, if you arrive in a hurry and you see, you look at the traffic light and it's red, and if I tell you it's normal that it's red because it's a machine, you're going to kill me.
No,
because you're going to say, I'm unlucky, the traffic light is red.
My next step, but that's my next step. That's what you want to say. You can still push the logic a bit further with the traffic light.
Yes, but I don't want. I'm giving the talk. We'll talk about that later if you don't want. I don't know what you mean, but okay. If you look at the way that mathematics, the importance of mathematics in the nature, of course, the classical theory, the Newton theory, for example, exhibit the conception of punctual point, which doesn't exist in nature, you know. And the best definition of the material point is given by Piero della Francesca in the books that my chairman who left mentioned a few days ago. And he says that according to geometries, who says it by imagination, the point is that part of which is not. That is, the point is that there is no interior of the point. That's a beautiful part. But if you represent a point, you represent a point by something like this usually. And in fact, from the mathematical definition of a point to this, there is only a certain deformation, not so much, you know. You just make the things a little bit more thick than the things. If you want to do what would be corresponding to this, which plays the role of a material point, what should be this, then you have no answer. You cannot have something, you cannot make a picture, you cannot design, you cannot draw a vector in a vector space by an image. This is totally impossible. This is what I mean. That is reference to Magritte, to saying this is not an electron, but truly this is not an electron, like this was not a pipe. So what I mean by this is that in quantum mechanics, you cannot, each time you make images of quantum mechanics, you go out of the mathematics. It's not that you go in the neighborhood of the mathematics, you just go completely out of the mathematics, and then you lose absolutely everything. So, almost last remarks is something which is in the movie by Godard, and which I think is also very well connected to the structure of quantum mechanics. Apparently, it's a phrase in the movie by Godard. He says that it's Monet who said that, but it's not Claude Monet. In principle, it's Proust, after seeing the painting of Monet, Bras de Seine près de Giverny, which is a very nice painting, of course. And Proust say, I say it in French because the traduction in English is almost impossible, at least for me, but I think in general. Il ne faut pas peindre ce qu'on voit, puisqu'on le voit. This means you shouldn't paint what you see because you see it. And il ne faut pas peindre ce qu'on ne voit pas, parce qu'on ne le voit pas. You shouldn't paint what you don't see because you don't see it. Il faut peindre qu'on ne voit pas, which that you barely translate by you have to paint that you don't see, but not that as the object complement of don't see, not that the things you don't see. You should paint the fact that you don't see. This is extremely subtle. And in quantum mechanics, each time you look at what you see, there is nothing quantum that you see, because quantum mechanics lives at a very small scale. At a very small scale, you don't see anything, and you just have to consider that you look at the fact of not seeing it, and this is the formalism of quantum mechanics with randomness, with projection, and all that. Okay, so this is my last slide. So what I think, and 1 century after the birth of quantum mechanics, so let me take 1 minute to say that in 1923, Louis de Broglie imagined that matter could be a wave. In 1925, Heisenberg invented quantum mechanics in the sense of the matrix theory. To do that, I don't have time to develop, but you know, Werner Heisenberg was very young, and he was subject to hay fever. So it was in May, and he went to an island on the North Sea where there are no trees, so it was not subject to hay fever. And later on he said, by joking, I'm not sure that Heisenberg had a big sense of humor, but he said there was nothing else to do on this island and invented quantum mechanics. But in fact, what he did, he was doing computation, let me be just a little bit technical for 1 second. A lot of perturbation expansion where we multiply function, that is, you make convolution. When you make convolution, you multiply and you sum on objects we define on 2 indices, I minus g. And you realize that in order to fit some formula, you have to turn the minus. That is to pass from something like b, I minus g, to b, I, and then you rotate this by 90, and the minus becomes a comma. And the fact that you have a comma now makes these 2 indices completely independent. This is a matrix, this is classical, this is quantum. And it appeared exactly like this because of a lot of computation he was doing. In 1926, Schrödinger show his equation, that is make a morphing between de Broglie in a certain sense and Heisenberg. Then there was Born interpretation of the wave function, and everything was packed in a single theory in a brilliant way by John Feynman, which was mentioned, I think, by you yesterday, who reduced all this phenomenological aspect into 4 axioms, which are extremely simple, extremely beautiful, and extremely efficient. This is really a performance. So what I claim is that if after 1 century of being unable to find the language for quantum mechanics, in France at one point, people were talking about the quantum, the morphing between electron and quantum, the quantum. 5 years, nobody talked about that anymore. There is no way of building a language for quantum mechanics, I believe, and in fact it was never done without talking about mathematics. But once again, the mathematics of quantum mechanics are that. basically that and only that. Everybody can understand this. So, you see, I call it Copernic 2 because it seems to me, and I can say it because it's not mine, it's a revolution which happened 1 century ago, that it's really a Copernic 2. That is the second Copernic revolution where the mathematics now enters inside, not outside as a language, but it's inside deeply ontological, the quantum mechanics. And let me quote this, another sentence by Einstein that I think he never wrote. Einstein was attending a conference by a very young Heisenberg, and Heisenberg at that time thought that he had seen the trajectories of electrons, because in bubble chambers you have something which looks like, and Einstein said no, because it's a theory, we decide what we have to observe. And his theory decides what to observe, then if you take this as a starting point, you don't have any problem, any paradox in quantum mechanics. Let me finish truly by a joke that people who are a little bit old, like me in France, will remember. It was a sketch by a very famous and very great humorist, French, called Fernand Reynaud. It's a sketch du tailleur. And if you translate this into quantum mechanics, you have the following, which explain socially why quantum mechanics is badly considered in a certain sense. Heisenberg goes to Taylor and asks for a suit. Taylor takes a charm. Heisenberg was big guy like this, and he say, comes back next week, your suit will be done. And Heisenberg left, and they say, Heisenberg, the Taylor say, but Dr. Kant went to me last 2 months ago. He ordered me a suit, Kant was like this, and he never went, so I'm going to give the suit of Kant to Heisenberg. So Heisenberg comes back, he tries the suit, and he says, well, I have a small problem here, and the Taylor says, maybe you don't behave well. Put your arm like this, it fits perfectly well. The same as, and at the end, Heisenberg goes out of the tailor shop, walking like this, completely, but with a suit perfect for him, And the morality is what? What say people in the street? People say, look how this man is built. His tailor is a genius to succeed making a suit which fits so well to him, So each time you hear somebody telling you that quantum mechanics can be interpreted or is included in the philosophy of Kant, think to the Taylor sketch and you will. Ok, grazie a tutti quanti, and once again, Margriet.